Hello everybody, welcome back, and thank you for coming to the last talk of this session. So I'm going to stand down here because I want to use the laser pointer and that doesn't work that well from up there. So I'm Moritz Große-Wentrup. I'm a group leader at the Max Planck Institute for Intelligent Systems in Tübingen in the department of Werner Schökow. And I'm not going to talk about how to train good decoding models, but I'm going to talk about how to interpret decoding models and how the interpretation rules for decoding models change relative or are different from encoding models. So when I say interpretation rules, I think the first thing that we need to address is what sort of interpretation rules do neuroimaging people really want to have? You know, there are different ways to interpret models. So I would like to start by taking a look at some quotes. And here's a quote from Trends in Cognitive Sciences in 2001, where the author writes, "Hippocampal activity in this study was correlated with amygdala activity, supporting the view that the amygdala enhances explicit memory by modulating activity in the hippocampus." Here's another quote from the Journal of Neuroscience from last year. "We tested whether pre-stimulus alpha oscillations measured with EEG influence the encoding of items into working memory." And I think there's an abundance of such examples in neuroimaging studies, and I'm sure all of you have read sentences like these in the discussion sections. And I think this illustrates two things. First of all, people want causal explanations. They want mechanistic explanations. They want to be able to say the amygdala something enhances a cognitive state, explicit memory, by modulating activity. Yeah? So they want causal interpretation rules. That's the first thing. And the second thing is that people all know that correlation does not imply causation. But in the discussion sections, we often see that people believe that somehow, maybe sometimes it actually does. So here, the authors start off with observational language, correlated, and then they move on to causal terminology. And here again, oscillations measured, and then the result is that something influences something else. Yeah? So, and we started wondering, is that actually allowed, or when is it allowed? So this presentation is about which causal statements are warranted and which ones are not supported by empirical evidence. And as it turns out, this is a very tricky question. And to dive right in, I want to explain to you why this is such a tricky question before I get to the nitty-gritty mathematical details. So in neuroimaging studies, we usually have a task that we give to the subjects. I denote this here by the T. And that might be something that they have to do, a stimulus that we show to them, something that we can randomize. And then we measure some brain state, X, from the subjects. And we may also have some measure of behavior, maybe the delay of a response or the error rate of a behavioral response. Yeah? And if we now train a traditional encoding model, then what we're looking at is we're looking at some features X and some properties of this X as a function of the class label, of the condition. And so we want to look at whether the mean response of voxels changes between two different class conditions, two different experimental settings. And now if we're in a task-based setting, this means that we're looking at properties of X given T. And because T is the task that we give to the subjects, we're here modeling the effect, the brain states, as a function of their causes, the task. Yeah? So that means that in encoding models, in a task-based setting, our models work in a causal direction. We're modeling effects as function of their causes. If, however, we go to the behavior-based setting, this is different because now we're looking at some measure of the brain state, or we're modeling the brain state as a function of the behavior, and brain states cause the behavior. So here we're now modeling causes as a function of the effects. So this model here, the encoding model in a behavior-based setting, works in an anti-causal direction. Now if we go to decoding models, then now we're modeling or trying to predict the class label as a function of the brain state. That means that in a task-based setting, we're predicting the cause, the task, from its effect, the brain state. So decoding models in the task-based setting are anti-causal models. And that is in contrast to task-based settings in encoding models where they work in a causal direction. And if we go to the behavior-based setting, this is again flipped. Yeah, so now we're modeling the behavior as a function of the brain state. So we're modeling the potential effect as a function of its cause, the brain state. So this is again a causal model. Yeah? So if you want to attach causal interpretation rules to our empirical results, then I think it's intuitively or should be intuitively plausible that this needs to be taken into account. We need to take into account what type of model we're using, encoding or decoding. And we need to take into account whether we're actually looking at tasks that we give to the subjects or behaviors that we measure from the subjects. And this has different implications for our causal interpretations that are supported by our data. Okay, so this is the first important take-home message. Be aware of this. So now getting a little bit more into the details, I want to start with the notation here. So the experimental condition C denotes the experimental condition, and that in my talk can be the type of stimulus that you display to a subject, maybe houses versus faces, and that might be coded as +1 for houses and -1 for faces. It might also be the delay of a behavioral response, then C would be some positive real number. As X, I denote my brain state features. These are n-dimensional vectors, and they can be anything. They can be your bold response set as m voxels measured by fMRI. They may be the band power at m EEG channels or the mean spike rates of m neurons. It doesn't matter. It's just the way that you decide to represent brain activity. And then in our setups, we usually have experimental data. Yeah? So we observe pairs of our experimental conditions and our brain state features, and we observe n instances of this. And we assume that these are drawn from some unknown joint distribution of our class labels and of our brain state features. And now I'm going to assume for the rest of the talk that we have an oracle for any property of this joint distribution. This means that whatever we want to know about this joint distribution, we know. And of course, this is not a reasonable assumption. Yeah? In practice, we have to estimate everything from data, and there are lots of problems involved in this because our data may not be IID and so on. But here for this talk, I want to talk about the theory. I first want to understand if we have perfect estimators for everything, what are we allowed to conclude, what are we not allowed to conclude. And when we have settled that and understood that, then we can worry about how to estimate these quantities in practice. Yeah? And in particular, for my talk, there are going to be two very important statistical concepts. The first one is statistical independence. That is written as C independent of xi, which translates into the joint distribution of these two variables, factorizes into the product of its marginals. And intuitively, this means that C and xi don't contain any information about one another. The second concept that is going to be very important is the one of conditional statistical independence. It's very similar, but here I'm going to say that, this means that C and xi do not provide any information about one another if I already know what happened at all other features except the ith one. Yeah? So knowing what happened with all the other ones, does xi still provide additional information about my class labels? And mathematically, this is then the joint distribution, the conditional joint distribution of C and xi factorizes again into the product of its marginals. So much about the notation. And now we need to talk a bit about causality. So I said we want causal interpretations. And when we talk about causality in neuroimaging, this is often a very fuzzy concept. There's dynamic causal modeling, there's Granger causality, the other different concepts of causality, and we want to be rigorous, so we should say explicitly which concept of causality we work with. And I work with the concept of causality by Judea Pearl and Peter Spertis, who both published their books on causality in 2000 and worked on that more or less independently. And I strongly believe these are the most rigorous frameworks for causal inference and causal statements that are available to us today. And Judea Pearl got the Turing Award, the Nobel Prize, kind of Nobel Prize for computer scientists for this a few years ago. So in this framework, we say that xi is a cause of xj, and we write this in this graph here with this arrow from xi to xj. If there exist values of xi and xj such that this thing holds. And I'm now going to explain what this means. Yeah, so here we have the distribution of xj. And here we have the so-called do operator. And that says that we intervene on xi. We take xi and set it to a specific value by doing something to xi. Yeah, for instance, stimulating the brain and setting some brain state to a certain value. And if this intervention here leads to a change in the distribution of xj relative to looking at it independently of this intervention, then we say that xi is a cause of xj. Yeah, so intuitively, if you intervene on a system, you do something to it, and this has an effect on another system, then you say the first one is the cause of the second one. And this effect doesn't have to be deterministic. You just want to be able to somehow change the probabilities of events occurring. And I think this is a very general concept and framework for talking about causality. It's very powerful because it's probabilistic, and it captures our notion that causes should have effects in the world. You can do something with them. Okay, and the three most important causal graphs in the framework I'm going to talk about are the chain, the fork, and the collider. Now, I'm now going to give you a very brief intro to causal inference in this framework, and this is tough. Yeah? So I've been reading this book by Judea Pearl for about 5 years. Now I'm trying to give the intuitive idea how this works in 3 minutes. So if you get the intuitive idea, this is great. Don't expect more. So each of these graphs here that encode certain causal relations, they give rise to certain observable relations in your data. Yeah? These graphs exist somewhere in nature, but we can't observe them directly. However, the causal Markov condition tells us that independence relations implied by such graphs are encoded in the joint distributions that are generated by these graphs. It seems a bit cryptic. It simply means that if you look at this graph and the data that is generated by this graph, for instance, the chain, then this implies certain independence relations between these variables. For instance, the chain says that x1 and x3 are dependent because x1 is a cause of x3 via x2. If, however, you already know what happens at x2, then x1 and x3 become independent of one another. Yeah? And these are quantities, these independence relations that in principle you can observe in the real world. You can see that in your data, while you don't have direct access to these causal graphs that generated this data. In the fork, you have exactly the same condition and dependence relations. The collider is different. In the collider, x1 and x3 are independent because there's no causal relation between the two. But if you condition on x2, so if you know what happened at x2, then these two provide information on one another and hence are dependent. Now, an important concept in this framework is the so-called assumption of faithfulness. So faithfulness says that the joint distribution over some graph contains no additional independence relations beyond those implied by generating DAG. Again, that's a bit cryptic. What it essentially means is that you can move from these observable independence relations to these graphs that you can make inferences. Yeah? For instance, if you observe these two relations in your data here, then you know that the fork and the chain are out because they are not consistent with these independence relations. And if, in addition, you're willing to assume that there are no other hidden variables present, and you want to assume faithfulness, then the collider is the only graph that can generate these dependency relations here. And so this allows us now to move from observable independence and conditional dependence relations to structures that can have generated your data. And this is kind of the gist of causal inference in this framework. Now, moving back to the introductory example by the anonymous author in the Trends in Cognitive Sciences. So how do we translate this into this causal framework? And to me, the statement the author makes here is amygdala activity was correlated with the hippocampus. So HC and AM, hippocampus and amygdala are dependent. And he concludes from this that the amygdala modulates the hippocampus and thereby enhances explicit memory. Yeah? So this is how I translate this sentence into this language of these DAGs. For this other study, we tested whether pre-stimulus alpha oscillations measured with electroencephalography influence the encodings of item working memory. That translates to alpha power and working memory are dependent. Hence, the authors conclude alpha power is a cause of working memory. And now the rest of the talk will be asking, are such statements correct? When are they correct? And if we can't say anything, what can we do about that? So all this now was about causal inference, causal models, but I said I'm going to talk about encoding and decoding models. And the link between causal statements and encoding and decoding models, that's still missing. And that's what this slide is about. So how can we move from encoding and decoding models that we use to causal inference statements? So in encoding models, we're modeling brain state features as a function of the experimental condition. So the question then that we're asking when we have such an encoding model is, does a certain brain state feature, xi, change across experimental conditions? Yeah? So we want to test the null hypothesis for each brain state feature, whether the experimental condition and the brain state feature are independent. And if we can reject that for a certain feature, then we say that xi is a relevant feature in our setting, and we wish to interpret it. In decoding models, we do this a bit differently. Yeah? So we're training a model to predict the class labels given our data. And the question that we're then asking is, which is the set or which brain state features actually help us in decoding the experimental condition? Yeah? So it's a bit of a different setting, how we determine relevant features in decoding models. And what we want to test really is we want to know for each feature xi, if that still provides additional information about the class labels, if we already know what happened at all the other features. And if we can reject this here, this null hypothesis of conditional independence, then we say xi is a relevant feature in our decoding model because it provides additional information on our class labels that's not yet contained in all the other features. And this is the, well, I would say, standard test for relevance in decoding models. And the way that is implemented in many toolboxes is that you first train a decoding model on all your data, and then you permute, and you obtain a decoding error, and then you permute one of the variables. So you make it irrelevant. You enforce that it cannot contain any information on the class labels anymore. Then you retrain the decoding model, and you check whether that makes your decoder worse. And if it makes your decoder worse, then you say, aha, this is a relevant feature in my setting. There are some problems with that. I'll get to that in the very end. So, and this now provides the link between encoding and decoding models and causal inference. Yeah? Relevant features in our encoding and decoding models translate into statements about univariate independence and multivariate conditional independence, respectively. And from the previous slide, I argued that these independence and conditional independence statements tell us something about the causal structures that may have generated our data, and hence form the link to causal inference. Okay, so this was the introduction. And I can now move on to causal interpretation rules for individual encoding and decoding models and for joint encoding and decoding models. In the first part, I'm going to say, if you look at each model individually, there's really not much you can say. So the first part is essentially saying be extremely careful about causal statements. Most of the time, you're not allowed to make them. And then the second part of the talk, I'm very briefly going to argue that to get out of this mess and maybe get a little bit better and make a little bit more stronger statements, we should start training encoding and decoding models jointly on the same data and look for asymmetries in these models. So let's get started. So now we're looking at features, xi, each individual feature. And this feature may be relevant in an encoding model, so relevant, irrelevant, or in a decoding model, relevant, irrelevant. And we distinguish between the task-based setting and the behavior-based setting. And the first thing we're taking a look at is the encoding model in a task-based setting where feature is actually irrelevant. So the feature is independent of the task that you give to a subject. And that's a simple interpretation. There's no relation there. So xi is no effect of t. This is simple. Causal conclusion, no effect. Now, for a decoding model, if you find that in a decoding model in a task-based setting, a feature xi is not important, it's not relevant, yeah? Does this mean that this feature is also not an effect of your task? Unfortunately, no, it doesn't. Because either these two might really be unrelated, or there could be this chain here. And this chain here, the task modulates xj, and xj modulates xi. And hence, xi is actually an effect of the task, but it doesn't help in decoding because all the information about t is already contained in xj. Yeah? So if you find that a feature in a decoding model in a task-based setting is irrelevant, you can't really conclude anything from that. You don't know whether it's an effect or not. So what about relevant features in encoding models in a task-based setting? So that is rather simple because you can randomize your tasks. You can really do a randomized controlled experiment, and if you find that some brain state feature responds to that and shows an effect, then you know that your brain state feature is an effect of your task. That's simple. However, in a decoding model, can we conclude the same thing? And unfortunately, again, we can't. because there are two graphs that can explain a relevant feature in a decoding model in a task-based setting. Either the feature can really be an effect of T, or we could have this collider structure, where this feature here helps in decoding T because it is conditionally dependent on T given xj. So you can understand this as some sort of noise variable that you can regress out. Yeah, for instance, subjects could get tired over time, and by regressing out the effects of subjects becoming tired, you can do a better decoding model. But this doesn't mean that xi has to be an effect of T. So, unfortunately, this is inconclusive. Yeah? And now, because I want to save a bit of time, I will not do the same level of detailed analysis for the behavior-based setting, but essentially it's exactly the same thing. So in the behavior-based setting, it's even a bit worse. Or maybe I should talk about one thing. Maybe this one here is important. What if you find that in a behavior-based setting, in an encoding model, that a feature is relevant, that really provides information? Can you then conclude that your brain state feature is a cause of your behavior? It's kind of the neural cause of it? No, you can't, because you can have this joint, this hidden confounder between that the xj causes your behavior and is a cause of this brain state xi, and then xi and b are dependent on one another. So inconclusive. Same holds for the decoding models. So now we have this table, this joint interpretation, this interpretation table for individual models. And if we now have some study or some data that makes a causal claim from some empirical results, we can say, okay, this is the claim, a feature alpha is relevant in an encoding model here. So we are in the behavior-based setting, because working memory is a behavior. We're here, we're in an encoding model, behavior, and the rule is no, you can't conclude this. Yeah? And I hope that this table will help us to be more informed about our discussion sections and be more careful in our causal statements. Because if you look at it, it's really quite a depressing picture. Yeah? So in most cases, you can't make any causal statements. You can only make causal statements for the encoding models. And then there's only really one causal statement here where we can say xi is an effect of t. And in all other cases, it's really inconclusive. So this seems a bit depressing because people believe decoding models can do a lot more, and you can obtain a richer interpretation with the decoding models than with encoding models. And here I would say no. But we can get out of this mess by training joint encoding and decoding models. Yeah? So we can take the same data, train an encoding model on it, train a decoding model on it, and then observe whether these models agree or whether there are asymmetries in the relevances of these models. And whenever there are asymmetries, then we can learn a bit more. I want to briefly illustrate this. So let's assume we're in a task-based setting. An encoding model finds a feature to be relevant, but a decoding model says a feature is not relevant. What does that mean? Well, this means that we have a so-called chain. The task modulates xj, and xj modulates xi. And hence, xi is relevant in an encoding model, but it's irrelevant in a decoding model because xj is in between t and xi. Xj already provides all information that you need. Yeah? So in this setting, we can conclude that xi is an indirect effect of your task relative to the other features. And this is not a particularly strong statement, but we have learned a bit more, just a tiny bit more about this. Conversely, if we find that in an encoding setting, a feature is irrelevant, but in a decoding setting it is, then we have again learned a bit, because we can now say, okay, xi is not an effect of the task, but it still provides information because it is some noise variable, or maybe some context variable that helps you to decode by adjusting your decoder to the subject's brain state or to some disturbances. Yeah? So in this case, we can say, okay, xi is a variable that provides some context. And the same distinction holds for the behavioral case. So you can learn a tiny bit more if you combine encoding and decoding models. So going back to this example in the beginning, Or we translated the statement, hippocampal activity is dependent on amygdala activity, hence the amygdala enhances explicit memory via modulating the hippocampus. If you go back to this table, there's really no support for this statement. Yeah? Just because these two variables are correlated, with one another doesn't mean that you have this chain here. However, this chain makes testable predictions. Yeah? This chain here implies that in an encoding model, amygdala activity and explicit memory are dependent on one another. So in an encoding model, you should find amygdala activity to be relevant. But in a decoding model, amygdala activity should become irrelevant because it only modulates explicit memory via the hippocampus. Yeah? Unfortunately, these conditions are not sufficient to conclude this model, but at least this model makes testable predictions that you can test, and you could reject this model if this is not met. Good. So wrapping up, there are, of course, certain caveats. Yeah? So this whole framework of causal inference is based on the interpretation of negative results. Because you find a feature not to be relevant, you conclude that there is a certain independence relation, and that is the basis of your arguments. But of course, you could only find your feature not to be relevant because you haven't observed enough data, or your statistical tests have not been powerful enough. And this is something you have to be aware of. Measuring more data, doing more tests might change your causal conclusions. I think that's just the way it is. That's the practical limitations that we have to live with, but we have to be aware of them. Second, this assumption of faithfulness that we need for these causal statements, that's untestable, at least presently untestable. And essentially, faithfulness says that nature is not fooling you. If nature wants to fool you, there could be causal pathways that exactly cancel each other out, such that there are causal links in nature, but you don't see it in your data because nature decided to hide it from you. And there's a mathematical theorem that says, of all the distributions in the world, those that are unfaithful have measure 0, meaning that you are very, very unlikely to ever meet such an unfaithful distribution in practice if you sample uniformly from all distributions that exist in the world. However, there's another more recent result by researchers from ETH Zurich that says that while these unfaithful distributions are really, really small in the space of all distributions, they have a strange folding through the space of all distributions, so you're always rather close to an unfaithful distribution. And that, again, means that it may be difficult to see dependencies in real data. Practical limitation. Then, the way that we test relevance in decoding models right now is usually based on these permutation tests. And they are not real conditional independence tests. They are biased towards dependence. The reason for that is that if you have two features in your decoding models that don't provide any information on your class labels, but they are highly correlated, and you permute one of these features, then you're breaking the correlation of that feature with this other feature. And this breaking of the correlation makes you believe in these permutation-based tests that your feature is relevant even though it's not. Yeah, so you may overestimate the significance of your features in your decoding models if you have correlated features. So the obvious solution to that is unbiased conditional independence tests, develop direct conditional independence tests. And there's a huge community working on that. It's very, very hard, but there's some progress, and I'm confident that over the next 10 or 15 years, we will have more powerful tests for this. Okay, take-home message. So my take-home message is, if you don't like causal inference, don't use it. Yeah? Causal inference comes with a lot of baggage, and you have to be aware of this. And I think there are really good reasons to abstain from any causal interpretations in your discussion sections. Fair enough. But if you believe that we are hunting causal mechanisms in neuroscience or neuroimaging, and we want to learn causally how brain states relate to cognition, then you need to make sure that your conclusions are supported by empirical data. Yeah? In many instances, you will only be able to check whether something is nonsense. But maybe in some cases, you may make a little bit stronger, you may be able to make a little bit stronger conclusions by being very explicit about the inherent assumptions. And I strongly believe that this is one way to go forward with understanding how the brain gives rise to cognition. Thank you very much for your attention. I'm looking forward to your questions. oh, wait a second, I should point out one more thing. These are the people who have been involved in this. Thank you very much to them. And if you want to read up the details of this, you can find it in our NeuroImage publication that came out, I think, in January. And I suggest you take a look at our author's copy on our webpage, because the NeuroImage copy is abysmal in its text setting. Thanks. So this is now the general discussion section, right? So you can ask questions about anything, not just about this. Hi, Jonas.
So I have just one small one. You always show examples with 2 or 3 variables, and indeed, if you do conditioning with your information, it's a 3-place relation. So how can you tell us a little bit how that generalizes for higher dimensional settings?
Yeah, so I always show these examples with 3 variables because these are often already sufficient to give counterexamples that certain conclusions are not valid, and hence you don't need to consider more. The statements where I argue that you can indeed make stronger statements, they are indeed also taking into account that you might have hidden variables, you might have other variables in there, and so this is implicitly taken into account. I just, for simplicity, didn't mention it here. There's one more thing, though, that I find very interesting. I'm only talking here about conditional independence tests, conditional on all other variables except one. Because that's the way that decoding models are usually analyzed right now. But there's no reason to limit yourself to such conditional independence tests on all other variables. You could also condition only on subsets of variables. Or you could test conditional independence between one set of variables conditioned on another set of variables. And indeed, if you take a look at how Judea Pearl and Peter Spertis are doing all their causal tests, then they don't limit themselves to only this type of conditional independence test, but they test on all subsets of variables. Of course, that is computationally expensive, but if you want to learn more about causal structures than what we have argued here, this is the way to go forward. But then probably you should be directly working with conditional independence tests and not maybe with decoding models.
This is a general question about causal interpretation. So is it okay to interpret it with respect to a model? So that's how most people do it.
Yeah.
That's always.
So it's interesting that for Judea Pearl, there's always a structural equation model underneath this data. So for Judea Pearl, structural equation models are kind of the whole basis for these arguments. And that's his starting point for presenting his theory. Peter Spertis and his collaborators say this also works without. You don't need to assume this. This is a framework that holds without assuming that there is any structural equation model underneath. And one result of that is that this causal Markov condition is an assumption for Peter Spertis and a proof for Judea Pearl. So these things can become very complicated.
Do you have any other questions or topics you want to raise or ask questions to the other speakers today who are still here? Most of us are here. If not, then I think they've had quite a long day, and we could do with a little bit of rest before the opening ceremony later on at 5:30 p.m.
Maybe I should say one more thing. I was approached by 2 guys who wanted to know about the MEG decoding and brain-computer interfacing as well. So I prepared that talk as well, and if you want to know something about it, please approach me anytime the next week. I'll be here all the time.
Okay, well, let's call it a day. Thank you for all the speakers, and thank you to you to stay here all day long and awake and questions and making sure that hopefully next year we also get to go on with the education. So I think there'll be some evaluations, so please fill those evaluations, because that's how the courses are rated. it helps also improving the course. And that's it. Thank you.
And maybe I would like to thank the organizer, Christoph, because it's really great that he's been organizing this for 2 years, inviting us. Christoph, thanks.